All right, I'll get you a head start on that. I'll take care of attendance. Kate, you got a quiz to make up.
Okay.
You gotta make up that quiz by Wednesday. If you don't take it on Wednesday, it's 0 permanently.
Can I do it today?
Sure. Okay, if we got time at the end of class today, it depends how quick we go through those examples. Have you seen Lily today?
Yeah, she's here.
She okay?
I think so. She's been here pretty much all day in all my classes.
Okay. Maybe she got checked out? I'll go mark her absent. If I need to change it, I'll change it. Thank you, Lily. Okay. 2 types of reactions when we're looking at enthalpy. It's either A, exothermic, or B, endothermic. Exo meaning to exit or to leave the energy, so energy is leaving the system. Or B is endo, is to come into, and so energy is going to go into the system. Okay. So when you are breaking bonds, I don't care what bond you're breaking, you're going to release some sort of energy. The bonds you then make is going to store energy. But we're going to look at, do you start off with more energy, or do you end off with more energy? And if you start off with more energy and you go down, it is exothermic. Or if you start off with low energy and you go up, it is endothermic. This is probably the most important part of what we're doing for the whole week. So, delta H. What does delta mean? It means the change. And then you have this other Greek symbol. Math class. You ever seen that symbol in math class? Maybe you have, maybe you haven't. It just means the sum of or total. So if we look at the total energy of our bonds broken, compare that to the total energy of our bonds formed, we can then look at how many joules or kilojoules of energy be released per mole. When we did the thermite, we're going to see a huge release in enthalpy. So it's an extremely exothermic reaction. We're going to release a whole lot of energy, so much so that that iron turns into molten iron, and then we'll eat through some sort of steel block. Hi, Lily. You all right? Mm-hmm. Okay. Okay. So delta is change, sigma is the sum of or total. So what we're going to do then is take that table I've given you, looking at the values of what energy did we start with, what energies we end with, and then we go from there. But we're going to have a little bit of a problem depending on how much rust we have on drawing Lewis dot structures. Evan, how much do you remember about Lewis structures?
Not very much.
Okay, we'll get there when we get there. Okay. Let's look at as far as a graph goes. Okay. One of these is endothermic, one of them is exothermic. So what we notice is, if your energy starts off, your total enthalpy starts off lower than what you end with, what we find out then is our change in energy, or change in enthalpy, is positive. Energy has to be stored. The opposite of it, if we start off with more energy and we end with a lower energy, our enthalpy is negative, I mean we're going to release some sort of energy. However, both of them have some sort of hump to get across, to go over. If that hump didn't exist, it would be a spontaneous reaction and it happened immediately. So what is going on here with this little bit? This little bit same thing here. This is what's called your activation energy. It's how much energy does it take to activate that chemical reaction. So when I mix in my 2 powders for my thermite, and I just set it on the table like that, it is not going to do anything. It needs to have some sort of energy to activate or to start that chemical reaction. So, thermite right here, I'm going to take a butane torch to it, get it nice and hot, increase the heat, start that energy, and then once the reaction starts, it's all downhill from there. So what does our thermite reaction look like? It's going to be a very steep drop off. Or July, it's going to burn through steel. Okay. Having you good so far? Okay, exothermic release, endothermic regain. How do we calculate it? So, is everybody good here? Okay. Because now we're getting into the meat and potatoes of what we're actually going to do here. I'm going to give you a chemical reaction. Hopefully you know hydrogen plus chlorine gas. You can predict it, HCl, donezo. Balance it, we're good. What you now have to do is look at what type of bonds are involved. So a hydrogen-hydrogen bond is a single bond. Chlorine to chlorine is a single bond. But now we have to look at, I have 2 hydrogen to chlorine bonds. These numbers right here in this table, I will never make you memorize any of them. Your job is to figure out which bonds you have, find these values, and then use them. Okay? If you get to the part where you're looking for these numbers, the hard part's done. All right? The hard part is probably going to be finding which bonds you have. But for this first one, I just gave it to you. Actually, I'll give you a second right now. I'm going a little fast. I'm going to slow it. And if you have a hard time writing that sigma, I just draw it like this. You will see sometimes it's done like this. I don't care. Some people just do the letter E. Okay. So our change in enthalpy of our reaction is going to equal the sum of the bonds broken. So I'm going to put it in parentheses right here. We have a hydrogen and a hydrogen. Oh, come on. What's going on? There we go. I'll just try this again. Whatever's going on, I blame it on Evan.
Why me?
I don't know, why not you? So we got one hydrogen-hydrogen bond broken. What else have broken, Evan?
CL.
A Cl-Cl bond, chlorine-chlorine bond.
And that yields,
So those are two bonds that we broke, right? What did we form?
2 HCl bonds.
Two HCl bonds. So I ran out of space. Let me zoom out a little bit. Maybe this will help a little more. Minus the sum of bonds formed, which is two HCl bonds. Go there? Or we just plug in our numbers. We're done. Hydrogen, hydrogen. What's that gonna be? 436.
Yeah.
What's chlorine, chlorine?
243.
243. Minus 2 times HCl, which is
432.
432. I know these numbers are a little bit different than what's on your table, but just follow me for the sake of uniformity. I'm going to use these numbers.
864.
Cool. Your right side's 864. What about the left side, Evan? Got 6.
679.
679. I agree with you.
679. Yeah.
Yeah, 679. 679 minus 1 or 864. What's that going to give me?
-2.
I believe it's that. Check on the math. 679 minus 864 gets me negative 185. Negative 185 what? Kilojoules per mole. Which means it's what kind of reaction?
Exothermic reaction.
Exothermic. So here's what I know. If I take hydrogen gas and chlorine gas and I mix them up in a container, put a little bit of activation energy into them, it will rapidly turn into hydrochloric gas, and it'll be an exothermic reaction, meaning it'll get hot. Alright, the heat of it will increase. If I know how many moles I have, then we can look at the change in temperature, but I digress. If you get to this number, you're done. We're looking good. You got here, Warren? Good so far? Because now we're about to go from 0 to 60. Because I'm not going to give you the bonds. We got to find the bonds. Everybody good here? I'm about to hit the NOS on it. I give you the reaction. You got to find the bonds. Once you know what bonds you have, then we're good to go. I got oxygen here. I got hydrogen. And I got water. I know in that table I've given you, I went ahead and give you the enthalpy value of O2. It says in there specifically O2. But humor me in finding the bond, if it's a single or double bond between oxygen. How many valence electrons are in oxygen? Remember that? 6. You got 6 of them, you have 2. So 6 times 2 gives me 12 valence electrons when dealing with O2. So we draw our Lewis diagrams. We give everything a single bond. And then we count our electrons, right? Everything wants 8. We give everything 8 except for hydrogen, because hydrogen's special and it only wants 2. So we got oxygen. Both oxygens have 8. But what's my problem in that picture? Kate, what's my problem? Do you remember how to do this? Bring on some serious rust. We got.
You have 14, don't you?
We have 14 electrons in the picture. So let's do this counts together. We got 1, 2, 3, 4, 5, 6. The bond counts as 2, right? So 2, 4, 6, 8, 10, 12, 14 electrons, but I only want 12. What do we do if we had too many electrons?
Get rid of them.
We get rid of 2, we make a double bond. Oh. There we go. Got 14 electrons now. We now have a double bond. We see why now, looking at this paper, we're not going to use, where's it at? I'm trying to do it on the back side. Well, we're not going to use this one right here, because that's an oxygen single bond. We're going to use this O2 down here, which means a double bond. So if you want to, you can scratch out that O2 and put like an O double bond O. If you want to, it's up to you. Okay, same thing for hydrogen. Let's do hydrogen now. Hydrogen has how many valence electrons?
2.
4.
1.
Oh, it's 2.
One of them, but I have 2. So 1 times 2 will give me 2 valence electrons in total. That's it, we're done, right? Hydrogen's only going to ever have a single bond. And the last one's going to be
8 valence.
8 in total, because we got 2 hydrogens, gives us 2. So we got 8 valence electrons. Oh, I'm getting ahead of myself. Oop. We'll try again. 6 valence electrons gives us 8 in total. Does hydrogen have 2 in the picture? Yes, both of them have 2. Do oxygens, does oxygen have 8? 2, 4, 6, 8. Yep. We're happy hunky-dory. We've now drawn our diagrams of these things. Let's find out the enthalpy. Johnny, you good so far?
Yeah.
Cool. Caden, you good so far?
Yeah.
Okay. Breaking off some rest while we're following along. Okay. Hudson, you good?
Yeah.
Okay. Did you do Lewis structures with us?
Yeah.
Okay. I couldn't remember. Alright. So now all we need to do is find the enthalpy of bonds broken versus bonds formed. So delta H of the reaction equals bonds broken. We're going to break one oxygen double bond, one hydrogen single bond, minus oxygen hydrogen bond. What did I do wrong here? I did something wrong. What do you got, Brian?
You only have 1 hydrogen for H2O. You only have 2.
I have one hydrogen for H2O.
Yeah.
One hydrogen oxygen bond?
Yeah.
Here.
Another.
Absolutely. We have 2 hydrogen oxygen bonds, so we needed 2 down here. Follow with me, Ev? Can you find my values for me? What's the oxygen double bond?
495
495
plus 436
436
minus 146. No.
Yeah. Second guessing is not making me feel comfortable.
What are we looking for? Because I don't see.
So we got oxygen double bond, 495, agree with you. Hydrogen and hydrogen, 436. We're looking for an oxygen hydrogen bond, which I might also be listed as hydrogen oxygen bond. So did you find that?
Hydrogen, oxygen. Okay, so 463. You say.
463. Boom, Bob's your uncle. Find the number. Run to my handy dandy calculator.
No.
126 for 462.
Yeah.
You say you got a finance already?
No.
Or just this right side?
Yeah, 463 is minus 926. Negative 926.
Negative 926.
Mm-hmm.
Cool. What about the left side? We get that yet? 495
That's 11.
plus 436. 931. What's 931 minus 926?
5.
5, right? 5. What? What's my units? Kilojoules per mole. So is this exothermic or endothermic?
Endothermic.
Endo. So we should expect this to be most likely getting cold, but not by very much. All right, we'll get a little bit cold. We good? We're legit good. We're looking leagues and bounds above third period. I mean, I'm a little concerned. We drew a Lewis diagram and went, it was like, oh, I spent 20 minutes on it. Can I do one more example and call it done for today? Yeah.
Okay, so for the water, you said it's the hydrogen oxygen bond.
Yeah.
So is that always gonna be the case? Or, like, is it always gonna look like that? The two OH whenever you write
For water.
for water.
Mhm.
Yeah. Okay.
We're about to another example. We're going to have different numbers of bonds pop up. It'll probably be very comparable to a difficult problem. Not difficult, I'd say tedious. Okay? Because there's a lot of areas you can forget to do stuff and make things happen. All right. Last example we're doing today. Two of these we already know what they are. O2 is oxygen double bond to oxygen. We just did that. And H2O is going to be HOH. Oh. Try again. We got to find CH4 and CO2. What's up, Putz?
Do you have to balance that first?
Yes, we got to balance it first. Took the words out of my mouth. It's like the next sentence. Don't forget to balance it. Should be pretty easy. I put a 2 right here, 2 right there. Bob's your uncle, and we're balanced. CH4, CO2.
Isn't it 8 electrons for CH4?
Yeah, because carbon's going to be 4, hydrogen's going to be 1 times 4, so 4 plus 4 gets you 8 valence electrons. I'm going to hop over here. Carbon's got 4, oxygen has 6, but there's 2 of them, which gives us 12. Oh, I'm writing one thing and mean another. So in total we have here is 16 valence electrons. Draw my carbon, put 4 hydrogens around it. Okay, how many electrons are in that picture?
8.
Absolutely. How many do I want?
8.
Are we done?
Yeah.
Absolutely, looks like it's done to me. Cool. CH4's done, methane's done, oxygen's done. Let's do CO2 now. Cool. What's the problem with the picture, if there is one?
There's too many electrons.
Too many electrons. So what are you gonna do?
Make those up.
Absolutely. I'm gonna erase. Let's go ahead and make a double bond here. Am I happy yet?
No.
No. So what are you gonna do?
Make another double.
Make another double bond. Make another double bond here. Nope. Ed, what do you think?
I think it looks pretty good.
I think it looks great to me. Everything's got 8 electrons. We have 16 valence electrons in total. Happy hunky dory, we're done. I now have all of my bonds. Johnny, you ready to big brain it?
Maybe.
Why did I draw 2 oxygens and 2 waters over here?
I don't know.
Oh, because there's a 2 in front of it in the balanced equation.
Absolutely. So, what I recommend doing is to redraw it. That way it's easy to count out your bonds. Or if you want to big brain it and just know when to multiply by 2, sure. But I found to be more helpful is just draw those molecules out and then just count your bonds. So delta H for our reaction for this third one is, what bonds did we break? We broke 4 carbon-hydrogen bonds plus 2 oxygen double bonds. What do we form?
Carbon dioxide and water.
2 carbon oxygen double bonds. And 4 hydrogen to oxygen bonds. Everybody see where I got my numbers from? Yeah, Evan, unless you did something wrong.
Where did you get the 2 and the 4?
2, this 2 and this 4, or this?
Those 2.
This one?
That 2.
Okay, so let's do it in yellow. We have 2 carbon oxygen double bonds.
Okay.
Over there?
Yeah.
And then we have
4 hydrogen.
1, 2, 3, 4
Okay.
of the oxygen hydrogen bonds. Cool?
Okay. That makes sense.
There we go. That's why I recommend draw them out. Because you can see them. Because sometimes people are right. There's other ways to do it, absolutely. You do what's comfortable for you. I find the most successful one is just drawing the molecules out. All we can do is plug in our numbers down. We're on our way to victory. Delta H of the reaction equals 4. What's carbon hydrogen number? Carbon hydrogen 413 plus 2 495 minus 2 carbon oxygen double bond
799.
What'd I do wrong, Evan? Where'd that number come from?
Multiple bonds.
Where'd I get 358 from?
a good question.
Single bond.
Shouldn't that be a plus? Like the C double bond O minus 4.
C. Yes, this should be plus. You're right. But where'd I get this 358 from?
The carbon and oxygen single bond.
Yeah, so I looked at the wrong value. I did the carbon oxygen C1 bond. That's not what I want.
So 799.
I want the 799 number for the double bond. Plus 4. What's oxygen hydrogen bond get me? 463. Plug in your calculator, you're done. So I love these calculators because I can just type it in all in one get-go, call it done. Bracket 4 times 413 plus 2 times 495, close bracket, minus 2, oh, I'll put a bracket on that, 2 times 799 plus 4 times 463. I get negative 808 kilojoules per mole. Seems like a big number, doesn't it, Evan? Kind of. Well, let's look at the reaction. What reaction do we have? What's
Combustion.
CH4? You remember this?
Carbon.
It is a hydrocarbon.
Carbon.
Specifically, it is
Carbon tetrafluoride.
yes, which is also known as, I'm just curious if you know, it's methane, which is a fuel source, combustion reaction. Absolutely, you should have some sort of heat being released. It's also the same gas that's in your farts. Alright? You light that stuff on fire? Absolutely. It's going to be an exothermic reaction.
Like parts on fire.
You didn't know that?
No.
Chemistry, there you go. There's methane in your farts. You can light it on fire if you want to. I wouldn't recommend it because you might go to the hospital if you do it wrong. There's a Darwin Award for you. Do you know what Darwin Awards are?
Stupid.
The rewards they give to people who died for stupid things, like lighting their farts on fire.
That seems like a very appropriate award.
Yeah.
Congratulations, you evolved as a species into this.